welcome students to a very short, brief introduction to ionic bonding. And today we're going to talk about what it means to be happy in terms of bonding, so that being full is to be happy, and that is to say a full outer shell, as we've talked about. Being noble is to be happy. So to get into a condition like the noble gases, which may have a full outer shell. And the name is bond, ionic bond, taken, not shared. So an ionic bond is when the electron is taken and not shared, which is different to the covalent bonding, which we'll cover in future lessons. So recap on valence electrons as we move from left to right. Down the groups, the first group, the alkalis, have one valence electrons. Then the alkaline earths have two. And then we move towards across the table. We'll go 3, 4, 5, 6, 7, 8. And the ones on the far right are nonmetals and they're noble gases. And they have a full outer shell, which brings a level of stability that all elements crave. How do we actually show these valence electrons in an easy manner? Well, we use something called the Lewis dot diagrams, which show just the valence electrons, and we'll use that to show the process of ionic bonding. So how does an atom achieve a full outer shell? Well, this move to a stable octet is achieved by the movement of electrons, not protons, not neutrons, rather the electrons that are whizzing around outside on the outside of an atom. So it's this movement of electrons that produces a charge in the case of ionic bonds, and those charges, if they're opposite, will attract. And that's where you get this bond from, and how compounds can become more stable. And there's more compounds than elements in the world around us, so obviously this happens quite a bit. So if we look at a periodic table, just a recap, metals make up most of the periodic table. They're in red. And the non-metals are in blue on the right-hand side. So if we look at one of the metals, lithium, highly reactive metal in the alkali metal group, lithium has 3 electrons, and we can see that it has just one valence electron, which is right on the outside shell. And lithium obviously is very close to having a full outer shell. If we can just peel off that outside shell, it will be left with the inside shell, which is full. And so what lithium is going to do is try to offload that electron to a element that is craving an electron, and very good candidates for that are over on the right hand side of the table, which is why the alkaline metals bond very, very easily with the halogens, because halogens just need one electron. So it's a match made in periodic table heaven. And so the lithiums are going to donate the electron to the fluorine. So the electron is going to jump across and onto the fluorine. Now when that happens, of course, what we will see is that this lithium has now lost the electron. It has a full outer shell now, but because of that, it has an imbalance in electrons and protons. It has one less electron than proton, and because of that, it gets an Li plus 1, but you don't generally show the plus 1. And the fluorine now has one extra electron than proton, and so it becomes an F negative 1. Okay, so what we're seeing is now we have charged ions. Those ions, which is very, very important. The final part of this is because they're negative, they're opposite rather, there's going to be bonding that's going to take place, much like a magnet would when you have opposites, or as we talked about in class, our favorite Hollywood stars seem to be following the route of opposites attract. Okay, so we see valence electron patterns like we've talked about. The metals are on the left. They generally form positive ions, just like we've seen. So sodium, lithium, potassium, calcium, magnesium, those metals on the left of the table, they are going to shed that electron, and because of that become positive ions. The nonmetals before bonding will gain electrons and therefore become negative ions. So your halogens, also oxygens, nitrogens, phosphorus, sulfur. And there's a bit of a pattern here which starts to develop. So The elements in group 1 will become plus 1. The elements in group 2 will become plus 2. In group 3 will become plus 3. And then the ones in group 4, the carbons and silicon, they generally don't take part in ionic bonding. They're right in the middle. They can take or receive electrons, and more so take part in the second type of bonding called covalent bonding. The non-metals, they follow this pattern, but they do it in reverse order. So nitrogens and phosphoruses will be -3. They'll take on 3. The oxygen and sulfur will take on 2, -2, and then the halogens will be -1. So you'll see this kind of nice step up, step down effect: +1, +2, +3, -1, -2, -3, -2, -1 rather. Okay. So just let's do a little bit of a discussion on what are the properties of ionic bonding. So what happens when ionic bonds form, or how do they behave? Well, ionic bonds involve the bonding between a metal and non-metal. It's very important. One atom loses an electron, one gains an electron. Electrons are transferred, which produce ions which have an opposite charge. It is very important to say that ionic compounds have no net charge, so those charges should balance within the compound. So you have a +1, a -1, they balance and become 0. And ionic bonds conduct electricity, so they are what's called, because they are electrical conductors, they are what's sometimes referred to as electrolytes. Okay, so they are good electrolytes. If we look this, there's an example, a BR example of a ionic bond where sodium has lost an electron to chlorine, or rather transferred one. You have a positive and negative ion which then attract, which is our common salt. And this ionic bonding forms a very rigid shape, which is called a lattice structure. And there's a diagram of the lattice structure. It's a very tight-knit bonding. So that's a BR version of an ionic bond. We can also show this using Lewis diagrams. So I'm going to use a potassium and a chlorine atom to work through how they would bond in a Lewis context. Okay, so we talked about the fact that the metal is going to actually lose an electron, so it's going to come in and it's going to sit, and the chlorine is going to gain that. Looks like we're one chlorine short. Whoops. Okay, so we're going to draw in one electron short. So chlorine started with 6 electrons, and it's gained a red electron, so the outer shell electron, from the potassium. Now, because of that, we can show that in Lewis, but in order to show it, we must add a couple of things. So they now have charges. So these are now ions. The way that we show it is we use square brackets, and we show the ionic charge. So the K became +1, and the chlorine becomes -1. And in ionic bonding, square brackets are used to show the presence of ions. So that's the Lewis dot diagram for the compound potassium chloride. So it is important to note that it's not always a 1:1 ratio. Just like there's 2 hydrogens and 1 oxygen in water, H2O, the same thing happens for ionic bonding. So when you've got a magnesium atom, it will want to shed 2 electrons to become 2+. So just like here, we've seen there's these 2 electrons, and magnesium is going to try and get rid of those 2 electrons, but if it's bonding to a chlorine, it can only get rid of 1 electron to each chlorine. So in fact, you're going to need 2 chlorines to get rid of those 2 electrons. So each chlorine will get 1 electron. And what you end up with, you can see it in the diagram, is the magnesium is going to shed 1 electron to each chlorine, so 1 here, 1 here. And because of that, there's 1 magnesium and 2 chlorine. So there's Mg2+, and each chlorine has a -1. And hopefully you guys can see that indeed the charges, when added together, become neutral. They become zero. And that should be the case. So the two chlorines, so you have 2 multiplied by -1, which is -2. And then you add the 2 from the 2 plus, and you'll get 0. Okay, so those charges should actually balance out. And that's a good way of understanding what's the ratio of each atoms and how do they combine. Always a good idea to, when you're trying to figure out how they combine until you get more comfortable with it, maybe draw out the Lewis or the BR diagram. So what about aluminum or aluminium, where I come from, and chlorine? In what ratio do they combine? And how do we show it with a Lewis dot diagram? Well, Lewis dot diagram can be a good tool to figure out how they combine, but let's try and do it without the Lewis. So we would determine the charge that each ion would have. Okay, so we're going to write out our atoms first. And we're going to ask ourselves, what are the charges? What charges are they going to have? So what ion is aluminum likely to become? Well, it's in group 3, and because of that, it has a charge of +3, and it will lose 3. It will become a +3. And therefore we can write out the charge as +3, and the chlorine we can write it as a -1. These are the ions that they're going to form, and we know that from the periodic table, or you can find out by drawing a simple diagram. And then we're going to balance the charges so they add to 0. Well, we can see we have 3 pluses and we only have 1 minus. So clearly we're going to need a couple more chlorines. Okay, so we're going to need 2 more chlorines to balance that out, where a +3 is balanced with a -3. And of course, if we're writing that, we're going to have AlCl3. That's how we would actually write that. Now there's another way to do it, which is called a crisscross method. So that is one way, just to tally them up and then rewrite them. You can also use what's called a crisscross method. I'm going to show you that very, very quickly. The crisscross method basically says write out the ions, and then you're going to crisscross those ions down, the numbers, not the charge, so only the numbers. So you brought the 3 down to the right and the 1 down to the left. So you get AlCl3. Of course, there's a 1 sitting in here that we don't show normally. And how do we show this with a Lewis dot diagram? Okay, well, when we're talking about Lewis dot diagrams, remember we start with our Al. And we have 1, 2, 3. And I'm going to show this very explicitly here so we can see the movement of electrons. And we're going to, each one of these chlorine is going to have 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. They're paired up, of course. And what's going to happen is each one of these is going to go to a chlorine. And the Lewis allows us to see that there will be, in fact, that transfer, and that there's going to be that ratio that's involved. Okay, and we're going to put them in so we can see them. You do not have to use color. I'm just showing you in color to sort of break them out right now. And we're going to have to use square brackets. Okay, -1, because when we show the Lewis of an ion, we have to show the charge with square brackets, and this is a +3. So we have Al +3, and all the Cl's have a -1. And that will be the case for all ionic bonds. They follow the same process in terms of drawing them using Lewis. So my question to you is, would you be able to draw a Lewis structure for sodium and sulfur? In order to draw the Lewis structure, the first step is you would need to figure out the ionic charges, and then you would need to figure out the ratio that they will bond in, and only then can you draw the Lewis dot diagram. Okay, so how do we name ionic compounds? Well, it's quite simple. Remember, ionic compounds are formed between a metal and non-metal. The metal is always written first, and the metal is the positive compound. the positive ion rather, and the non-metal is negative. Metal is written first, non-metal second. Step 1, you write down the symbol for the metal, and then you write down the name for the metal, and then you write down the name of the non-metal, but you change the ending to "ide." So a simple example would be sodium fluoride, where you had sodium and fluorine. Sodium comes first because it's the metal, and you just write out the name of the metal, and then you change fluorine to fluoride. But be aware that there are some non-metals which don't follow the convention. They have a slight changing in the way that they're worded. So oxygen becomes oxide and not oxygenide, or something to that effect. Nitrogen becomes nitride, and sulfur becomes sulfide. You're just going to have to remember those ones. So for example, magnesium and nitrogen together bonded ionically, the compound would be magnesium nitride. Okay, so tomorrow we're going to do a little bit more work hands-on in terms of practicing this, and that's it for ionic bonds, and we'll move on to covalent bonds over the next couple of days.